In this video, I want to tell you about the osculating circle. Now, a quick Google search, and I find a definition for osculate. Actually, two definitions. One was one I expected to be to kiss. To osculate is to kiss. But they also give a mathematical definition. So a curve or a surface touch another curve or surface so as to have a common tangent at the point of contact. So two curves osculate if they have a common tangent at their point of contact. So the osculating circle is the kissing circle. Now we've seen that circles are related to curvature in the sense that a circle of radius r has curvature equal to 1 over r. So likewise, you could think of a curve with surface with curvature k, you can think of as approximated by a circle of radius 1 over k. Right? This sort of best fit circle is what's called the osculating circle. If you think about a point on a curve, like I have my pen here as being the curve, pick a point. There's a lot of circles that could be touching right at that point. The question is, which one is the osculating circle? And it is the one that is in the plane of the unit tangent vector and the unit normal vector. Okay. So it will be a circle of radius k, and the center is at, well, the point of contact would be r of t, but then move over a distance 1 over k in the direction of the normal vector. Okay? So for instance, here, I've got the curve y equals x squared minus 4. Okay? And we calculated in a previous video that this curve would have curvature 2 right here. And so the circle of curvature has radius 1/2. So the unit tangent vector is pointing out this way in the positive x direction. The unit normal vector is pointed straight up the y-axis. So I went a distance of 1/2 in that direction, and I put my circle of radius 1/2. And you can see that that looks like a really pretty good fit for the curve right there at that point. Now, I also have in red here another circle at the point 2, 0. This curve has, the black curve there has curvature, I think it was 17 to the 3/2 power divided by 2 was the curvature. And it's about 35, just over 35. So I went in the direction of the normal vector, and the slope here is 4, so the normal vector has slope 1/4, so negative 1/4. So in that direction, I moved out 35, which is, I don't know, out here somewhere. And then I drew a circle of radius 35, so it goes right through that point. And that's the red curve that you see here is actually part of a circle. And at that point, that circle is a pretty good approximation of the curve. That's the osculating circle. Now I want to show you an example in 3D. So here I have an example where my curve is cos t, sine 3t, so x, y, and z are those. It's the black curve that you see here. I would call it a Lissajous curve. It just kind of goes back and forth, vibrating in the x direction and the y direction and the z direction. And it's that curve there, which just happened. Okay. Now I also have drawn the unit tangent vector in red, the unit normal vector in blue, and the binormal vector in purple. So you can see those there. But I also have a brown circle, which is the osculating circle. So you can see at any point along the curve that it's calculating this osculating circle. And I find it kind of interesting in that I've had this file on my faculty website for years, and just as I was preparing to make this video, I realized I was calculating the curvature wrong. So my circles were not the right radius. You can see on those tight corners the circle gets really small, but when it's kind of moving through these straighter sections, the circle gets really large because it's a very small curvature, and so it's a very large radius of curvature. Right? I was thinking about this point right out here where it was really, yeah, big like that. Right? Small curvature, big radius of curvature, so the osculating circle is large. So the calculations are down here. The tangent vector is the derivative divided by the length of the derivative. And then I had a mistake here in that I had the curvature being the tangent vector divided by the length of the derivative, when I should have had the derivative of the tangent. It's the length of r prime, length of t prime divided by the length of r prime, and I had a t there, so I was calculating the curvatures wrong. Once I straightened that out, then it looked a lot better, and the circles of curvature really looked much better. So anyway, there's your circle of curvature for all the different points on the curve there. I could watch this. It's kind of mesmerizing. Anyway, there you go. The osculating circle.